So welcome. Thank you guys all for coming. I am Mike Burkhart. I am a technical product manager for NVMe over TCP and VMware integrations, which I won't be talking about the latter, but the former is high praise for this talk. And also performance updates. And I feel like, first off, can I get a round of applause for the other speakers today so far? Because that's like, you guys, it's hard to follow. So hopefully I'll do it justice. So we're going to be talking about NVMe over Fabric with enhancements between Squid and Tentacle. So Tentacle is going to come out targeted later on this year. Squid is currently out, latest, greatest. There are a couple of things that I'll mention that are actually merged to main right now. So you can go out and try it out and whatnot, but just know that it's not, it's not Tentacle official until Tentacle is released. So first and foremost on NVMe over TCP, who is familiar with NVMe over TCP? Oh, I love you guys. When I do this talk, sometimes I get like two hands, and I'm like, okay. So, what's that? Yeah, that's actually what I normally say. Like, NVMe over TCP is what iSCSI wanted to be when it grows up, right? And it really is. Like, honestly, I cut my teeth on actually an AX150 Clarion, and that was painful. Guess how I learned about IOPS? Yeah. And also using iSCSI attaching to a VMware 3.0 ESX cluster. So, but dealt with VMware since the 2.0 days, dealt with Clarion since whenever AX150 came out. iSCSI was fine, but we had gigabit networks, right? We didn't really have the bandwidth and scale. You'd have to do multiple gigabit links, and then you'd have either bond or round robin or whatever type of mechanism you use to use those aggregate links. But it never really was true aggregate throughput unless you use some sort of customized multipath active-active driver, right? So NVMe over TCP, we take advantage of current high bandwidth networks, 10, 25, 40, 100 gig, right? So modern data centers have much more throughput to offer. And on top of which, it's just built upon RBD, right? So Rados block device is the underscoring volume that we write namespaces on top of. So it's very easy. And you're going to see, I've got a slide later on that shows kind of API mapping commands. This is not emulated. It's a pure write-through to NVMe. So it's highly performant. It's pretty awesome. So for those of you that don't know, so Rados block device, again, that's our RBD volume. Resides upon librados, which is your library providing access to Rados, which Alex said it before. I'm not going to say it. NVMe over TCP is just our gateway. So it's like RGW or MDS, all right? NVMe over TCP is just a net new gateway that we've introduced to Ceph. So overview of that. So you're going to have, kind of like iSCSI, you have initiators and targets. So you're going to have an NVMe, and you're going to see NVMe OF, which is over Fabric. And then NVMe over TCP is specifically the implementation that we have used for Ceph, right? So this is NVMe over Ethernet. NVMe over Fabric is the whole umbrella specification that includes things like RDMA, Rocky, again, TCP as well, and other things. So NVMe over TCP, we have initiators. We have our gateways are the targets, right? And those are going to reside on top of Rados block devices, RBDs, on top of your Ceph cluster. So that's a high-level conceptual architecture. Here is an eye chart. Circles and arrows. Let's focus on the important parts. So this is the stuff that we already know about RBD, right? So we've got OSDs, MONs, managers, pretty typical Ceph cluster setup. RBD images being presented. And then on the left-hand side, that's going to be our NVMe over TCP integrated as an RBD client. So the gateway itself is a client to Rados block device. So it's an RBD client that layers on top of it NVMe namespaces. Okay? So put this all together, it's really complex. But when you look at the fact that this already exists today and we're just adding a little bit on top of it, it's actually pretty simplified. And it's getting simpler as the versions go on. So that's another reason that I'm here today, is because we can show some of the progressions we made. I already said namespaces are mapped to images. Subsystems. So a subsystem is just a sandbox It creates a space around namespaces. You have what are called NQNs, so it's an NVMe qualified name. If you remember iSCSI, it's an iSCSI qualified name, or IQN. So similar look and feel there. Subsystems wrap around namespaces and NQNs in providing security boundaries and providing boundaries for access of data. So those namespaces live in a subsystem. They're brokered by controllers. The controllers are on a thread-based or reactor core-based model. I'll show you that in the slide. But basically, each initiator and target session is given its own controller for data transaction, right? So every data operation goes through its own thread, and they're all operated uniquely and distinctly on core. This is what that looks like a little more granularly. Now, the reason I'm bringing this up is because it's important to show performance enhancements and how we've actually leveraged this model. These are one-to-one associations, so every time you have an initiator target connection, that's going to be mapped to a controller. Controllers are going to have I/O queues, completion queues, and then an admin queue. Right? So we've got admin for disk access and canceling queues or canceling commands, et cetera. We've got I/O queues for executing and completing disk operations, right? No controller-wide sequencing, so this doesn't have to do any sort of massive hardware operations. It's just single thread, single core reactor, no reassembly constraints, no shared state across the queues, so there's no, race conditions or any sort of triggering that needs to happen. This is all kind of a one-to-one map, and they're ephemeral. So once that session is ended, they're done. Controllers go away, right? So we're not taking up cores that we don't need. And as they're instantiated, they're going to kind of roll through, right? So every new session is going to create a new core thread, and the old ones are going to expire and kind of roll off. So why is that important? Let's go back to the API mapping for NVMe to RBD. We have natively supported commands. Almost all of the native NVMe commands for disk operations are mapped directly to RBD commands. So this is a pass-through. So these disk operations exist today. It's not emulated. There's not latency. There's no injection in the path. It is just, this happens, right? We pass those on. We do have some emulation happening for commands that did not exist for RBD. That had to happen, right? The reason that abort has an asterisk next to it is because it's actually an older NVMe spec. We have NVMe cancel that's been introduced. Abort was in the data path. Cancel is actually in the admin queue. I don't know why we had a get rid of a disk command in the disk data queue. Hey, I didn't mean to do this. Are you doing that thing? Probably better over in the admin queue. So makes more sense to do that. The reason I'm showing you guys all this stuff, there are going to be two things that we talk about. One is going to be the reactor core scaling. Okay, so we saw that reactor core model. Every instance, every connection is going to be mapped to a reactor core. And controllers have reactor core scaling. We can modify those parameters, so we can kind of tune them a little bit. And then there is a command called bdevs per cluster, which is how many librd clients you dedicate to your NVMe gateways, okay? And as you tune these parameters, they come in pairs, right? This is how many cores you're gonna dedicate to reactor, or to controllers, sorry, not reactors. How many reactors you're dedicating to your controller. And then how many librd clients can you dedicate to those threads, right? So these we can modify, but also you're gonna see that these are gonna change coming in technical as well. So what's new? What is that? That's not a cuttlefish. What is that? Yeah, just it's another cuttlefish? Man, this. I'm not embarrassed. That's not my. I'm not a marine biologist. So in Squid, we had gateways in tech preview. Single gateway access to volumes. There was no HA, no failover. Discovery was not supported. 256 namespaces, very limited, right? There's a gateway CLI, but that was actually separate from Ceph ADM, so it was not native to Ceph as a package. And Ceph ADM support, you can create and run new gateways, but not manage them and administer all of the life cycle of those gateways. So, and technical, so there's going to be HA support, failover, and load balancing. Those are going to happen automatically. Load balancing will happen on failover and on maintenance. So as soon as you have one gateway either go out of service, just blink out of existence, it'll have a quorum, and it'll heartbeat, and they will discover, other gateways surviving it will discover, and the ANA groups are going to be redistributed across the living, surviving gateways. We only had a single gateway group. A group is just a shared configuration across multiple gateways. And previously it was only 4 gateways. So it provided some high availability, but it wasn't really scaling, right? It didn't really have a whole lot of flexibility. We have 4 gateway groups currently, and 8 gateways in a group, and can get up to 32 gateways per cluster, right? So that's a whole lot of throughput, and that's not actually, there's no limit to namespaces per gateway group or something like that. Those maximums are kind of separate from each other. So security, we have in-band authentication, so that's going to be DHH MAC CHAP. So if you're familiar with that in iSCSI and hate it like I do, it's much easier in NVMe over Fabric. Just so you know, again, this is all based off of SPDK, which is open source. It came from Intel and a consortium of other groups that worked on SPDK as open source. It is now in the custody of Linux Foundation, so we've got a really good group just running with it right now. That being said, the security nature of it was heavy consideration, right? So namespace masking is another one. So a namespace is just your volume, it's just your disk, right? And masking means you can have NQNs, a single NQN to a disk. So I can say, all right, I have one host connecting to one namespace, and I can security isolate them from an actual initiator perspective. So that leads to a multi-tenant model, leads to higher security, just a lot of good gravy there. MTLS, so we communicate behind the scenes in cluster communication. It's going to be gRPC, but gRPC in the broad open we know is not secure, so we use MTLS to encrypt those communications. And then for a client side, TLS PSK is available. That I believe that actually should have been in Squid. I'll have to double check that, but TLS PSK anyway. The problem is going to be your initiator. So Red Hat has been back and forth with TLS PSK. Other versions of Debian, Ubuntu, like it exists in some form, but like the full end-to-end encrypted network channel has been variable depending on whose initiator you're using. So your mileage may vary. Check that out. Scalability, we really ramped up. So we had, I think it was 16 subsystems in a group. And again, remember that security boundary for subsystems. 128 now. So again, goes more toward the multi-tenant model, goes more towards like I have a dev environment, I've got tests, I've got backup images, or maybe a prod refresh to dev or some sort of move like that, right? So I can have multiple different versions of subsystems and access to different disks, different security models within those subsystems. 1,024 namespaces, which sounds like a lot, but I want more. So we're gonna have more. That's not up to me. But so this is 1,024. We're actually, so on the development side, pushing really hard to get to over 4,000. And that was just a limitation with iSCSI was like 1,000 per, I think it was 2,000 per cluster. Keep me honest here, old school iSCSI guys. So anyway, so we're trying to push that as far as we can just to increase density on the cluster. And then 32 gateways in the cluster, we know about that. Dashboard administration. So anyone use a dashboard in here? Oh my gosh, no one wants to do it now. Oh, but okay, yeah, we got some.
I've done it.
Yeah.
For NVMe over Fabrics?
Yeah. Oh, great.
Works great.
Thank you. I didn't develop it.
I've done it both ways, and obviously in pre-sales, it's much nicer to demonstrate that to a prospect in the dashboard experience.
Yeah. So there is dashboard parity with the configuration operations, but again, CLI API is going to be, for a lot of people, it's going to be easier. It's got a known functionality. I can type it up, send it off, done. Alerts, it's kind of boilerplate, right? We'll have to have alerts. We have to not have stack traces. We're trying to figure out what that means. And then testing and toothology upstream. So all of that available with, I believe testing and toothology is already happening as well. So there's a lot of this stuff that's kind of a precursor. But Tentacle is going to be line in the sand. This is all available. So digging a little bit deeper into some of these functionalities. Load balancing. So we already talked to you about, it's rebalanced load across gateways in the group. You're looking at scale up, scale down events. So again, you got NIC failure, host failure, switch failure, what have you, right? Wherever your gateway communication is interrupted, you're going to have namespace connections rebalanced to the surviving gateways. You may have some disk path data path interruptions, but for the command queues that were alive and processing, they can commit, and the ones that weren't will retransmit because of the TCP protocol anyway. So maintenance upgrades, NIC failures, unplanned outages. If there are other states that suck, it will probably handle those too. So initial assignment is where we are today. We're really looking at load balancing, because load balancing, again, you have to understand, like, what is your load, right? Are you talking about sessions? Are you talking about actual throughput? Are you talking, like, how do you measure that, right? So today, currently, it's measured by sessions, because that's one of the easiest ways to balance load is just say, yeah, let's round robin and make everything fair. Future, we're looking at doing load balancing based on actual load. So it makes a little more sense just to have that throughput and balance across multiple gateways. Gateway priority assignments. So this is interesting. We talked about stress. Again, I feel like everybody that talked today set me up really good to talk to you about this stuff. Like, it's like, oh, it's stretch clusters. Cool. Gateway assignment. Like, awesome. Gateway priority. Well, why is that important? Stretch clustering. Why would I have a priority on my gateways? Well, one's in site A and one's in site B. It might be important to know where it is, right? So this one's my priority for this localized client, and I enable local reads and all that kind of good stuff. Never the twain shall meet unless there's a failure. Great. Well, we're not there yet, but we're getting there. So priority assignments is awesome. ANA group assignments, that's more of a subdivision. An ANA group is basically the failover pair that your NVMe gateway has for an NVMe, for a namespace session, right? So I have an active state for an ANA group, and that means my NVMe disk is being read and written to over on this gateway, and then the other standby state in that ANA group is on a different gateway. So right now, that just happens round robin. Failures happen, host 1 goes down, but 2 was my standby, 2 is now active, host 3 is now my standby, and it just kind of goes that way. We want to make that user configurable, so it makes a little more sense for maintenance, it makes a little more sense for pairing or even stretch clustering as well. So, cool. I'm going a little bit fast. I have a lot of slides, so please feel free to just jump in with questions, right? No big deal. Yeah?
I have a quick thing. On the ANA, are you always doing one active and the rest standby, or are you doing multiple active with multiple standby?
One active, one standby.
Okay.
Yeah, because that's so what's interesting about that is that the gateways are really taking care of the redundancy. The ANA group is just where is that redundancy executed, right? So the gateways are all active. The ANA group is where does this go when it fails? And that's, yeah, so there, to have, so like something like ADD or ADNN, I believe it's called, is like the full active for ANA namespaces or ANA states. That is something we've kicked around. True active multipathing is difficult. So, but I don't know more than that. I got really smart people I talk to. So, but yeah, that is something we kicked around. It's more been based on availability of gateways and availability of data instead of the true full multipath from NVMe. But that's something on the horizon, I think. So, good question. Appreciate it. Let's see, management, dashboard workflows. So we talked about this before. Basic configuration for all of the features that you're going to have for NVMe. So the service itself, so you got to start the service and scale it across the cluster. Pretty standard for most Ceph services. Subsystem, so how do we create a subsystem? It's going to have an NQN because it's effectively a target or part of it. Gateways, where do I scale gateways to? Because that's going to be your your target network port and IP. Your listener service, it's kind of tied together, but you can create all of these through the gateway as well as through CLI API. Creating namespaces, RBD images attached to namespaces. What's interesting about this is that you can take an RBD that has never been presented over NVMe, map it to a namespace, and then present it over NVMe over TCP, and that data is the same, right? Disk boundaries, logic, all of the access is fine. As long as that operating system that's mounting it can read that file system, you're off to the races. So this is important for something cool I can show you in a little bit. So, that we found out early stages, and it was like, all right, great, this is really good to know for migrations, for copies, for other cool things. So add, remove initiator, masking, and NQN masking per subsystem. That's, again, all of that stuff is normal lifecycle management for NVMe. So dashboard workflow. So I just figured I'd throw something out there. It's like, you've got, this CLI is very long. And unless you want to copy paste it, which you're welcome to, but then you have to kind of backtrack and replace the IP, and then you got to make sure it's okay, the port's fine, but then the NQN I need to change. Okay. Or I can clickety, 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 I'm done. Right? So you can tell I like things easy. So, but there's reasons why you would do both, right? The CLI, you're going to be able to, again, wrap through automation. You're going to have ability to, go through a whole cluster and set it up in seconds versus 17 million clicks. So for and against, right? This is migration from Fibre Channel to NVMe. This is one of the cool things about RBD mapping straight to a namespace. So we've worked on a process to basically migrate block data from any Fibre Channel SAN LUN over to an RBD image and then mount it as a namespace. That's important for many different reasons, right? And it's not just like a traditional either like virtual machine or like bare metal workload, but just as a total migration strategy, right? You're moving entire volumes and entire, the block device itself. So bare metal workloads, OS initiator, focused storage. VMs don't need this. So if you're doing this on VMware, you can storage vMotion. If you're doing Proxmox, you can do migrations, et cetera. So, but again, really, really cool to find out that was, and all this is making a network block device, mounting it over the network, and then using RBD migrate and pulling that in. And we've actually modified RBD migrate to have more consistency. So if the operation fails in the middle, it's going to recheck. And then also you can do your MD5 hashing, or we can do checksums afterwards just to make sure that all of your data is consistent. So this is what it looks like in practice. Just source JSON. I've got my network block device mounted. Here's going to be the RBD migrate prepare, import only. Source spec path is my source JSON, and then here's my destination target image. Here's my this is the pool that it's in, and then target image is going to be the namespace. Or sorry, not the namespace. That's the RBD image. And then afterwards, you can see under the status of the target image is done. Watchers none. Migration prepared. And then off to the races, right? You can check your checksum and then good to go. Make sure that matches. I found that one out the hard way. No. Yeah.
What's the difference between like RBD import and RBD migrate?
I don't know.
Yeah, because like it's good we have what we call live migrate, which is not live migration.
Yeah.
I was wondering how it happens.
So solid questions. I will answer the kind of the abstract, which is this process isn't live migration necessarily, though will be a cutover for sure. The other portion of that is the cutover is really like it's not during that preparation and migration. It's going to be after you've already moved because it's a non-impactful copy. To answer your question, though, what is the difference between the import and the migrate? I'm not actually sure. I think they might be similar operations, but I don't know under the covers what that.
Like RBD mirroring, that's if you're volume is live.
Okay.
Migration, is I think for volumes for that happen.
I guess
Okay.
when you're doing this, you have to tell the client, like, you got to shut off the VM or whatever. You got to shut off the thing.
You don't have to.
You don't have to.
No, this is, you can do this real time. This is, I mean, again, the data is mounted over fiber channel. It's read and written over the SAN fabric. This is just making a network block device through that OS, and whatever OS is attached to the LUN. So that's going through the network side. So the VM itself or the OS or whoever's contacting that LUN, they can actively read and write to it through their own storage drivers while spitting out the data through the network.
Yeah, like, how does it know, like, if you copy the first 10 megabytes of this, and then, like,
There's deltas. There's a delta. I think there's a delta check at the end. I'm trying to, magic. Let me double check. So again, like there's the prepare is basically you need to wrap this image so you can spit it out over the network. So I think it's like an image based, like this is what it is, and any bits after this we'll have to figure out, right? So, but that is fair. Like, so it's potential that if you have an active workload that's like database, yeah, you wouldn't want to do this and be like, oh yeah, it's fine, you know. So I'll have to double check on the prepare versus migrate, but fair enough. Cool. Other questions? Nope.
You mentioned you're using the SPDK versus the NVMe, the standard target, NVMe target that comes with the Linux kernel. Was there, some background on why that decision for the SPDK driver was chosen versus one that ships with the kernel?
I don't know the history there. I actually do know one of the research developers that started in on it in like 2021, I think, but I haven't been able to get on her calendar. So, but that's a fair question. I think if I'm going to ideate, there was a large consortium of very big vendors and great minds working on SPDK, and it was founded by Intel and supported with funds by Intel, right? So it was one of those like, okay, there's big support for that, that's moving, and then, again, being supported by Linux Foundation now, it's still kind of similar story, but that would be my guess, right? But good question.
Thanks.
Once I get on her calendar, I will let you know more. Grafana dashboard, so total pivot. So we did not have any Grafana dashboards introduced previously. These are, they're available now upstream. Probably having more developed, it's just a matter of like working through the backlog and seeing what's important, what's priority. But currently, performance and health are going to be the two top that most people are going to look for, right? So you're going to say like, hey, is this performing well? Am I getting expected IOs and throughput? And then also, what do I have? I don't love having this picture because it says warning on my slide. I'm like, why don't you say healthy? You could have said healthy. That's fine. Shows that it works. So, what's that?
This is the reality.
Yeah, it's too real. We all know that things eventually will go this way. So those are available. Should be available today. You should be able to find them in the code base. So Crimson backend. So I think who's heard of Crimson? I think probably a lot of it. No. Okay. Wow. Okay. Crimson is effectively revamping the OSD backends and how they work. So reducing footprint, performance, and reducing complexity. So I think there was like a 2.5 gig reduction per OSD or something like that. It was something. Dan, keep me honest here because I know you've seen Crimson. There was something crazy. No, okay.
I know Josh is there now, and
Okay.
I'm like, how is it looking? He's like, it's gonna be okay.
So the next slide.
Sorry. For those who don't know Josh, they've been like, that's the highest level of praise.
Yeah. Yeah. When Josh says it's going to be okay, that is like, if you were on a sinking ship, Josh would say, it's going to be okay. Like, or you're on the highest mountain, you've climbed there, it's going to be okay. Like,
UK English, it's like, it's all right. That means that's like the highest level of praise ever.
yes. I have a friend whose father used to say everything was fine. When, hey, how do you think this is? Oh, it's fine. But he was born in the 1930s. So fine meant like a wine, fine like jewelry. But she was like, I was born in 1980. Fine means it's all right, So it all depends. So it's fine. Let me talk to you about something that's better than fine. Fast EC for block and file. So again, like I said, you guys kept on setting me up for just awesome reveals here. So I will not be the math person. K&Ms, I understand. I don't know how to walk through that math, but I am positive Steven does. So you can talk to him about that. What I do know is that we have gone through iterations of partial stripe reads, partial reads, partial writes for the stripe on EC to optimize for block and file, right? So erasure coding for object and for that side of the house, works perfectly well and is very efficient. But like we saw earlier today, file and block kind of suffer because it's not what that was meant to do. Normally you'll see replica 2, replica 3 on block side or more if you're doing stretch cluster and multi-site. So M2 is recommended for block and file workloads. Larger chunk sizes improved for small block read performance. And then S3 workloads, object's not really going to benefit from this a ton unless you've got small objects because it's doing those smaller reads and writes, right? Partial and half stripe. So backfill for rebalancing should be much faster. And then minor scrub and descrub enhancements for EC pools.
Mike, is this using the ISA plugin?
I believe so. I believe it's ISA. I'll double check on that. Yeah. So talked a little bit about this. So partial reads, partial writes, partial metadata, partial delta writes, no padding of objects. I mean, again, on the block side of the house, we don't really want padding. Same thing for file. You've got an exact size. So savings for objects that are not of a multiple stripe width. And then on down, minor scrubbing enhancements, metadata consistency, and then CRC checks for deep scrub. This one's also, again, we talked about failures earlier today. And when an old OSD is available, backfilling getting one shard instead of K+1. So instead of getting 4, right? If your K is 3 and you've got a 3 and 3 or 3 and whatever, you've got 1. So much more efficient for the backfill operation. And this is what I'm excited about, charts. No, I'm kidding. But what we can see, so can you guys in the back see, can you tell the letters and wording? Okay, I want to make sure that it's a little small. Okay. So I'll describe this. So random read-write 70-30 split for 4K, IO depths 124, 256, so that scaling IO depth. The dotted lines are all squid, and the dotted purple line is for replica 3, so that, and lower is better, right? This is the latency for your operations. So dotted purple for replica 3, and then solid purple on tentacle for replica 3. They're both pretty much the same, right? So replica 3 is high performant, low latency. The solid lines are EC for tentacle versus your dotted line for squid. So they have much lower latency and much better performance profile. So really what that means, and again, we're not seeing millions of IOPS, it's not meant for that, but for tens of thousands of IOPS, for dozens of thousands of IOPS, we're still doing sub 2 milliseconds. So for block, that's going to be suitable for database workloads, right? So for a lot of high performance. And then similarly over here, so random read-write 70-30, 32K size, and then various depths. Again, since your size is a little bit larger, you're going to see a little bit sooner latency on the curve, but still more performance, a little bit better. Showing a little more similar curve to squid, but EC42 is a lot more improved. And then we can also see, again, the latency curve for the straight lines are a little bit better. So it's pretty cool. Not going to be for every workload, not going to be for every pool, but for block and for file, this will give you some better density. This will give you some cost savings. So you're not going to have 3 copies of every object everywhere, or 3 copies of every block or VM or whatever. You're going to have whatever your EC profile is, right? So solid improvement. No.
That's the answer.
Oh. Okay, what's the question?
Does one simply update from squid to tentacle and benefit from all of this goodness?
One does not simply update from squid to tentacle.
It's like a new layout.
Yeah, it is. So you're hitting the nail on the head. It's really, you cannot migrate from one to another pool. You can't upgrade the pool policy. You have to create a new pool to enable this. There's actually a command line flag that you have to say enable new, and I forget what it is off the top of my head. I might have it in here, but you have to specify. So, yeah, sorry.
We've got live migration.
You do. It's magic. So performance. So that's a little bit more on like performance-wise for erasure coding, but performance testing. I've got performance testing for NVMe over Fabric, right? So I wanted to be specific about that. I have from Reef, I believe, to Squid, and then also I believe newer numbers. Let's find out. So first, iSCSI versus NVMe. So those of us that have worked with Ceph iSCSI, we love it. It works great. No comments. Or that's me being sarcastic. iSCSI and Ceph was not as performant as we would like it to be, right? And this is where NVMe, we really ramped up and tried to make sure that it filled the need for block workloads. RBD has always been performant, right? It's always done a really decent job. But again, so looking at our hardware, we wanted to do as close to non-gateway, so close to native performance for RBD as possible. Hardware sets, 8 nodes, 56 cores per node, 100 gigabit network, 4 3 terabyte disks per node, 2 SDs per disk, so slicing and dicing on the NVMe side, and then 8 node cluster on Quincy. So it's 2023. We did performance testing in 2023, 24, and we have a run scheduled for this year as well. So that run should be on Tentacle. So I'm trying not to kill you guys with charts. The important part here is this bar is iSCSI. iSCSI did not scale with adding nodes, adding OSDs. It just flatlined. That's just where it's at. As a direct contrast, NVMe scales linearly except for this one outlier because of replica 3 on an 8 node cluster doing 8 times 8 jobs at the same time. So we double dipped on some nodes, so it went down on that very last test. But otherwise, again, you're going to add nodes, add OSDs, you're going to see linear scaling on NVMe. And that's 8 nodes, 300,000 IOPS versus sub 100 for iSCSI, right? So very big improvement. We ran another, this is on, so IBM Ready nodes, but they're Dell Ready at 760 XD2s. So 7.1 GA, it's same thing as Squid, same code as Squid. Newer nodes, 100 gigabit network, same. More disks, more OSDs, right? So 1 OSD per disk this time. And then, it's tested on a Reef. And then the initiator was on VMware for block workloads. But you could test this on bare metal as well and get similar results. There is some translation happening within the hypervisor, but for the most part, and it's probably even harder to see on this one. But the tests we ran, so 4 node, 8 node, 12 node, they're all fully populated, 24 NVMe drives, 1 OSD per drive per node. And then doing a 16K read-write at 70-30 split. That's the bottom blue line. And then random read-write at 4K is our yellow-orange. I say it's orange. Some people tell me it's yellow. But anyway, nearing about a million IOPS on multiple random workloads on a 12-node cluster with 24 NVMEs per node. So pretty awesome. Now this is not your 1 million IOPS per single instance type of rate, where Ceph is still distributed. But this is for full data center block workload. This could be on VMware, it could be on Proxmox, it could be bare metal, it could be database workloads, what have you. So you're still going to see similar performance because of NVMe based on RBD, right? The one factor I want to point out is, again, going to be your block size. Your performance will scale up and down with your block size changing, and that's just how math works. So, so here, again, we saw in the previous slide, we had 8 nodes on Quincy, and the 8 nodes got to about 300,000 IOPS. Starting out on Reef, we have a 4-node cluster on 390, right? So even more improvements just per software version. So this one is what I dictate is up spaghetti. But the good thing is that, so these normally, when you're doing performance testing, your latency curves you're gonna hit a wall, but you do not want to see curling back. You don't want your tromboning, right? So I don't want to lose performance if I start having latency issues. And we're not seeing that at all, right? We're scaling up. We're going to hit sub 2 milliseconds for 4 nodes, 8 nodes, and then 12. Sub 2 all the way to about 450. For 8 nodes, it's almost 650. And then, again, here's your almost, it's pretty much 900,000 on the dot for those 2 millisecond mark. This is, again, single BDEV per cluster. So this is a single libRBD client per reactor core, right? So by default, there's, I believe, a 20 sessions per libRBD client for the gateway. If we tune that down to 1, that scales the libRBD clients, and that allows more throughput. When we talk about reactor cores, this is tunable. By default, it's 12, so that's 12 CPU cores dedicated to gateway operations. You can tune that for your cluster as well. We're actually working on, one, the BDEVs per cluster is going to be automated. That's as soon as you deploy your gateways, they're going to be round robin across your gateways. And so libRBD clients are going to be per session, and that's going to scale automatically. The reactor cores are still going to be tunable because for smaller clusters, you don't need as many, right? For larger clusters, you will need more. So makes sense. That's just a JSON file. You can just inject it when you're deploying gateways, or you can redeploy them and tune them up, tune them down as you want. So we like, yeah, I got some thumbs up, cool. And this one's a little more granular chart, but I love showing it just for the fact that we have total IOPS and then sub 2, because again, in your block workloads, everyone's gonna ask, well, can we have low latency? Right, well, it depends on what low latency is. We can do sub 1, sub 2, sub 5. These are additive, so your total is gonna have all 3 of these. 1 is just individual, 2 includes 1, and 5 includes 2 and 1, right? So total IOPS on a 4-node with 4K block size, 797. Again, the way that math works, 16K is gonna be a little bit less than 32. We didn't have 64K runs until we got to the larger 12-node size. It didn't really make a total impact until we got to larger size, more OSDs. So, yeah. So again, I mean, really cool numbers. Again, like I said, like this is what iSCSI wanted to be when it grew up, and every version we're making iterations and strides towards more performance. So it's pretty cool. We've got a performance cluster dedicated to doing regression tests every release, and even updates when we do some specific operations. So pretty rad. So tuning considerations, know your workload, knowing your throughput, IOPS, megabytes per second, read-write ratios. All of this can filter into QoS as well. I didn't talk about QoS, but QoS is available on a per host basis, per namespace. You can do read-write ratios, IOPS, and megabytes per sec, read per sec, write per sec. Know your capacity, water is wet. Right? No total size you need. And latency tolerance. So I regularly, in the systems world, like hybrid cloud, most people don't know these, like, oh yeah, I need this total and I need this many IOPS. And it's like, well, you need to know your 95th percentile, you need to know your spikes, your dips, your lulls. How does your workload react during a month run, during an end of month close, or end of year, or hey, your major sales runs, or whatever those systems are. So kind of know that. Reactor cores, according to client-side needs. So, like I said before, smaller cluster size, less clients. You're not going to need as many reactor cores. If you have more clients, more need for access, more namespaces, scale those out and you get more performance, right? Then BDEVs per cluster, like I said, this is asterisk because this is automated and technical. It's going to kind of be a non-issue. So, someone tell me why I made that a pop-up? Why? I don't understand. Whew. Anyway, I guess I needed a break. High performance workloads, we already talked about more CPUs better. scale OSDs and nodes. You can also do, like we saw before, multiple OSDs per NVMe drive. And that all depends on, kind of capacity, fault domain, lots of different factors, how you would deploy and design that cluster. So high throughput networks are Ceph's best friend. The caveat here is that when we pushed our performance tests to the max, it was actually CPU cores that ran out first. We pushed a 100 gig network to about 92 gigs per second, gigabytes per second, or gigabits per second, but did not push it higher because our procs were 99% and everything was throttled. So pretty cool. I guess a cool burnout test, but at the same time I was like, really? So I need more than 12 servers to push that, okay. So, and this is just a link to our performance best practices and whatnot, and Ceph NVMe performance should be on the Ceph.io website as well. So thank you, Anthony. Highlights. This is all, your mileage may vary. This will change, right? Currently what's supported, it's not RHEL, it's just Linux. So any Linux initiator, VMware 7 update 3 and above, Proxmox, whoever has an NVMe initiator effectively, right? And then also SmartNICs, Pensando hardware. We're also working on integrating with other, so AIX is coming out with an initiator. Windows, oddly enough, has one that they're working on right now. It's a mixed mode world that we live in, so we're trying to fit every use case we can. API CLI and GUI available today, and then these we already talked about, gateways, subsystems, et cetera. So, and that is my time. Thank you.